Welcome to The Explainer. Today we're setting the stage for an exploration into what I think is one of the most fascinating and totally hidden engineering challenges of our lifetime. We hear all about the deployment of solar panels and wind turbines, right? But behind the scenes, there's this massive transformation happening in how we actually manage the flow of electricity. We're talking about the hidden technical hurdles of renewable energy and the complex, invisible world of grid stability. Let's get into it.
So, here is the million-dollar question. Can our power grid actually survive 100% renewable energy? We're all aggressively pushing to decarbonize our electrical grids, but can our current infrastructure actually handle the transition we're demanding of it? It's not just a matter of building more wind and solar farms. It is a fundamental physics problem that could literally determine the reliability of the power we depend on every single day.
Okay, let's dive right into this. With wind at about 30% and solar PV at 35% in some aggressive scenarios, we're looking at a huge win for the climate. But this influx introduces a hidden technical dilemma. We're completely changing the underlying nature of how power is generated. We are moving away from heavy, rotating machines to stationary, weather-dependent technologies.
Part 1. The Green Energy Paradox. It's a fascinating conflict between cleaner energy sources and inherent grid weakness. Let's take a look at what we're actually trading away to get this clean power.
Well, while we are successfully and necessarily removing fossil fuels from the equation, we're also actively removing the invisible shock absorbers of our electrical grid. You see, traditional power plants don't just provide electricity. Their massive, spinning physical bulk provides a critical stabilizing force. We're trading that heavy physical mass for lightweight power electronics, and that changes absolutely everything about how the grid behaves when things go wrong.
Part 2. The magic of grid inertia. To really grasp this paradox, we need to understand how traditional power grids actually maintain their delicate balance, second by second.
System inertia is quite literally the heartbeat of grid stability. Think of a massive, heavy truck rolling down the highway. If it hits a pothole, its sheer momentum carries it right through, smoothly and almost entirely unaffected, right? That heavy truck represents the massive turbines in traditional coal, gas, or hydro plants. Their physical, rotating masses naturally and instantly resist sudden frequency changes in the grid. They stabilize the system against disturbances before digital controls even have time to react.
So here is the crucial contrast. Synchronous generators act as our heavy trucks, providing inherent physical inertia. But inverter-based resources, or IBRs, like your solar and wind farms, connect to the grid via power electronics. They don't inherently spin in sync with the grid. We're essentially swapping out our heavy truck for a lightweight sports car. Sure, it's sleek and clean, but without that mass, that sports car is going to feel every single bump in the road. Part 3. Symptoms of a weak grid. Because when the grid feels every bump, things get precarious really quickly. Let's look at the actual consequences of losing this physical mass on a macro scale and what a weak grid actually looks like.
This breakdown of instability sources in renewable-dominated grids is incredibly telling. Low system inertia makes up a massive 35% of the instability pie. When generation drops unexpectedly or demand suddenly spikes, a low-inertia system just can't absorb the shock. This leads to terrifyingly fast frequency deviations, often referred to as a high rate of change of frequency, or ROCOF. If that rate drops too fast, automated protection systems kick in and parts of the grid just shut down entirely to save themselves.
Now, the mathematical drama playing out here is wild. As we push past 50% renewable penetration, frequency deviations spike sharply. At 10 or 20%, the traditional plants left on the grid can still handle the bumps. But as renewable penetration climbs higher, the stability margin just plummets. This is the exact engineering hurdle we absolutely have to clear to hit our climate goals safely. Part 4. Virtual inertia to the rescue. Don't panic, the story doesn't end in blackouts. We're going to shift the tone right now to the cutting-edge engineering solutions being deployed to literally save the grid. If you map out these stability issues, you can see exactly how engineers are tackling these mathematical crises. For frequency instability caused by low inertia, the mitigation isn't going back to coal. No, it's advanced technology. We're using techniques like fast frequency response and something incredibly clever called virtual inertia control. Let's break down exactly what those mitigation tools look like out in the field. We are literally replacing physical mass with digital reflexes. Virtual inertia control uses complex algorithms to instantly adjust an inverter's power output, effectively tricking the grid into thinking there's a heavy spinning mass there. Then we have grid-forming inverters. Instead of just following the grid's voltage, they actually establish the voltage and frequency themselves. They act as the new pacemakers. We're also strategically placing battery energy storage systems to inject power in milliseconds. And occasionally, we even use synchronous condensers, which are basically massive motors that spin freely without generating active power, solely to provide that much-needed physical reactive power and inertia.
Part 5. The digital substation era. But here's the catch. None of these solutions work without lightning-fast communication. Let's move to the final piece of the puzzle and see how this builds into the physical infrastructure of the grid itself, the substations.
Because a low-inertia grid is so incredibly sensitive, it requires communication at the speed of light. If a disturbance happens, the old method of analog copper wiring sending signals back and forth, it's just way too slow. This is where the new digital substation architecture, specifically the IEC 61850 process bus, comes in to save the day. It allows grid protection devices to react in mere milliseconds.
Data travels through a modern automated process bus in 4 exact steps. First, advanced optical sensors capture the raw voltage and current data out in the yard. Second, devices called merging units digitize that analog data right there at the source. Third, that digital payload is published onto a blazing fast, redundant fiber optic Ethernet network. And finally, intelligent electronic devices, the protective relays, subscribe to that data stream and can react instantly to isolate faults or trigger those virtual inertia responses we just talked about.
To really give you an idea of just how precise this digital network is, consider this number, 256. In this architecture, those merging units can sample data at an incredibly high rate of 256 samples per power system cycle. Not per second, per cycle. That is the level of high-frequency, high-resolution power quality monitoring required to keep a lightweight, renewable-dominated grid from tipping over.
Bringing it all together, there's this quote from the International Journal of Innovative Research and Technology that perfectly summarizes our core thesis today. The findings highlight the importance of advanced control strategies and improved system flexibility to ensure reliable operation of renewable-dominated power systems. The green energy transition isn't just about putting up solar panels. It relies entirely on these advanced digital controls and system flexibility. We are actively rewriting the physics of the power grid, swapping steel and steam for silicon and software.
Which leaves us with one final critical thought to chew on. We know the technology exists to stabilize a 100% renewable grid, but physical infrastructure is notoriously slow to build. The technology is racing ahead, but are we upgrading our grid fast enough to catch the wind? Thank you so much for joining me for this explainer. I really hope this sparked your curiosity about the hidden digital world keeping our lights on.